720 million years ago, the Earth died. Not in fire, not in collision, not in the violence of a meteor strike or the rage of a supervolcano. It died quietly, incrementally, in the most patient and relentless way the universe knows. It froze, not partially, not at the poles, not in the seasonal rhythm of ice ages that would come much later in planetary history. The Earth froze completely, from pole to equator, from the deepest ocean surface to the furthest reach of every continental interior. Ice kilometers thick covered a planet that had only millions of years before basked in tropical warmth at every latitude. This is the story of Snowball Earth, the most extreme climate event in the 4.5 billion year history of our planet. A glaciation so total, so uncompromising, so geologically violent that scientists spent decades refusing to believe it had ever happened. The evidence was too extreme. The mechanism seemed impossible. The implications for life were too catastrophic to accept, and yet it happened, twice. To understand how the Earth froze solid, you must first understand the world that existed before the ice. The mid-Proterozoic Earth was a warm planet, not dramatically different in its basic architecture from the Earth we know today, plate tectonics operating, oceans covering most of the surface, an atmosphere thickening with oxygen from billions of years of cyanobacterial photosynthesis. But the supercontinent Rodinia dominated the geography of this ancient world, positioned largely in tropical and equatorial latitudes, its enormous landmass creating a planetary geography unlike anything before or since. Rodinia was beginning to break apart. The same tectonic forces that had assembled it across hundreds of millions of years were now slowly pulling it to pieces. Rifts opened. New ocean basins formed along the fracturing margins. And as the supercontinent fragmented, fresh rock was continuously exposed to the atmosphere along thousands of kilometers of new coastline. Fresh rock and atmosphere do not simply coexist. They react. The chemical weathering of silicate rock consumes carbon dioxide. As CO2 is drawn from the atmosphere into chemical combination with weathering minerals and eventually carried to the ocean floor as carbonate sediment, the greenhouse effect weakens. Global temperatures drop. This process, the weathering of rock-consuming atmospheric CO2, operates continuously on a geologically active planet. But the fragmentation of Rodinia exposed an extraordinary quantity of fresh silicate rock along low-latitude coastlines where rainfall and chemical weathering rates were highest. The drawdown of CO2 was faster than volcanism could replace it. The greenhouse weakened. The planet began to cool. Ice began to form at the poles. This is unremarkable. Ice forms at the poles whenever global temperatures drop sufficiently. But ice has a property that makes it unlike almost any other material on the planetary surface. It reflects sunlight. A planet with extensive polar ice reflects more solar energy back into space than a planet without it. This reflected energy is energy that never warms the surface. The planet cools slightly further. More ice forms. More sunlight is reflected. The planet cools again. Scientists call this the ice albedo feedback. What it means in practice is that once polar ice begins to advance sufficiently toward lower latitudes, it can trigger a self-reinforcing cascade. The more ice exists, the more ice forms. The cooling becomes self-perpetuating. On the Earth of 720 million years ago, the feedback ran without restraint. Ice sheets advanced from the poles. They moved toward the tropics across what had been warm ocean. They crossed the continental interiors. They advanced onto the equatorial coastlines of the fragmenting Rodinia. And then the model suggests something almost impossible to visualize. The sea ice reached the equator itself. The ice albedo feedback, once the sea ice extended to within about 30 degrees of the equator, became unstable. A threshold was crossed. The remaining open ocean surface was too small to absorb enough solar radiation to resist the advancing ice. Within perhaps 10,000 years, a geological instant, the equatorial ocean surface froze. The Earth was a snowball. What this looked like from space is almost impossible to reconcile with any experience of the planet we inhabit. A white sphere. Brilliant, reflective, cold. The albedo of a fully glaciated Earth would have been approximately 0.6, meaning 60% of all incoming solar radiation bounced straight back into space without warming anything. The planet's surface temperature averaged somewhere around -50 degrees Celsius. At the poles, the ice was kilometers thick, grinding and flowing over whatever rock lay beneath. At the equator, the ice may have been thinner, perhaps only hundreds of meters in places, but it was ice nonetheless. The ocean below it was dark and cold and largely still. Life was not absent, but life had retreated to the most extreme margins of habitability that Earth has ever offered. Where did it survive? The debate continues, but several refugia are plausible. Hydrothermal vents on the deep ocean floor maintain liquid water regardless of the surface conditions above. The same volcanic heat that sustained deep ocean life for billions of years before the freeze continued to operate through the Snowball event, maintaining small warm environments in absolute darkness beneath kilometers of ice. Microbial communities that had evolved to exploit volcanic chemistry would have found their niche unchanged. At the equatorial surface, the ice may have been thin enough in some locations for dim light to penetrate. Photosynthetic organisms capable of surviving on extremely limited light may have persisted in thin films of liquid water within or beneath the equatorial ice. Some researchers point to the possibility of small liquid water environments near volcanic islands where geothermal heat created local melting, temporary open water patches surrounded by ice in every direction. The critical question is not whether life survived. We know it did, because the world after Snowball Earth was teeming with it. The question is how. And the answer speaks to something profound about life itself. It does not merely adapt to environments. It persists through catastrophes that should, by any reasonable calculation, eliminate it entirely. It finds the margin. It occupies the crack. It continues. For approximately 50 million years, the Earth remained frozen. 50 million years. The interval separating us from extinction of the non-avian dinosaurs is 66 million years. The Snowball Earth glaciation persisted for a comparable span of time, a duration so immense that it contains within it entire geological epochs of ice, darkness, and cold. And yet the mechanism that ended it was already operating from a first day of the freeze. Volcanoes do not stop erupting because the surface is covered in ice. The plate tectonic engine that drives volcanism operates in the mantle, far below any surface conditions. Throughout the Snowball Earth, volcanoes continued to emit CO2 into the atmosphere. But the normal feedback that removes CO2, chemical weathering of surface rock, had effectively stopped. Ice-covered rock does not weather chemically. The rock beneath the glaciers was insulated from the atmosphere by kilometers of ice. Weathering rates collapsed to near zero. CO2 therefore accumulated in the atmosphere throughout the glaciation. Not quickly, volcanism is a slow process, but continuously over tens of millions of years. The greenhouse gas that had been drawn down to trigger the freeze was now being rebuilt molecule by molecule, year by year, decade by decade, across a span of time that dwarfs all of recorded human history by a factor of thousands. Eventually, CO2 levels reached a threshold. The greenhouse effect strengthened. The ice began to melt. Once it started, it did not stop slowly. The same feedback mechanism that had driven the freeze into a runaway now operated in reverse. As ice retreated, more dark ocean surface was exposed. Dark ocean absorbs solar radiation that ice would have reflected. The ocean warmed. More ice melted. More ocean was exposed. The warming accelerated. Within perhaps a few thousand years, again a geological instant, the ice retreated entirely. What followed was unlike any climate event the Earth has experienced before or since. The Snowball Earth ended not into a world of normal temperatures, but into a world of extreme heat. The CO2 that had accumulated over 50 million years of volcanic outgassing without weathering removal was still in the atmosphere. Its greenhouse effect, now combined with the full exposure of a dark, ice-free ocean surface, drove global temperatures to perhaps 40 or 50 degrees Celsius. Hypercanes, storms of extraordinary violence, swept across superheated oceans. Chemical weathering of rock, now fully resumed, consumed CO2 at extraordinary rates. The planet oscillated violently between glacial and hyperthermal states as the atmospheric chemistry sought a new equilibrium. And into this violently destabilized world, drenched in nutrients released by the melting of billions of tons of glacial sediment, came life's response. The post-Snowball Ocean was an explosion. Every nutrient that the glaciers had ground from the continental rock over 50 million years, phosphorus, iron, nitrogen compounds, poured into the post-glacial ocean in the meltwater. The biological productivity that followed was enormous. Eukaryotic life, which had survived the freeze in its refugia and spent 50 million years of selection pressure filtering out all but the most stress-tolerant lineages, now found itself in a nutrient-rich, oxygen-rich, warm ocean world. The Snowball Earth did not merely test life. It transformed it. The organisms that survived the freeze were not average representatives of the Proterozoic biosphere. They were the ones capable of tolerating extreme cold, extreme darkness, extreme nutrient limitation, extreme chemical stress. They were, in the deepest evolutionary sense, the toughest life that had yet existed on Earth. And the nutrients and oxygen that greeted them in the post-glacial world gave this hardened biosphere the resources to do something it had never done before. It built bodies. The Ediacaran period that followed directly on from the Snowball Earth deglaciation saw the first complex multicellular animals in the fossil record. Dickinsonia and Charnia and Cloudina appeared in the rocks of the post-snowball world, the first complex organisms to leave their shapes in stone for the world 500 million years later to find and wonder at. Whether the Snowball Earth directly caused the Ediacaran explosion of complex life remains debated. The evidence for a causal link is suggestive but not settled. What is clear is that the most extreme climate catastrophe in Earth's history immediately preceded the most significant biological transformation in Earth's history. The frozen planet and the animal planet arrived one after the other in geological time. The Snowball Earth happened not once, but at least twice. The Sturtian glaciation, beginning around 720 million years ago, lasted for approximately 50 million years. The Marinoan glaciation, beginning around 650 million years ago, lasted for perhaps 15 million years. Some researchers propose a third, the Gaskir's glaciation around 580 million years ago, though this may have been less globally complete than its predecessors. Each glaciation was followed by cap carbonate, a distinctive pale limestone layer deposited directly on top of glacial sediment across every continent where the rocks are preserved. These cap carbonates are the geological fingerprint of the Snowball Earth. They represent the rapid drawdown of atmospheric CO2 in the post-glacial hyperthermal, as chemical weathering consumed the CO2 surplus in a geological blink. They exist in rocks in Australia, in Namibia, in Canada, in China, in Scandinavia. On every continent, the same pale layer sits directly above the glacial debris. The Snowball Earth left its mark in stone on every piece of land on the planet. We mine those rocks today. We walk across ancient cap carbonates exposed at the surface in outcrops around the world. We drill through them in oil and gas exploration. We study them in laboratories and argue about their chemistry and their deposition rate and what they tell us about the atmosphere of 635 million years ago. What they tell us, at the most fundamental level, is that our planet has already survived the worst. The Earth has been frozen, completely, globally, for 50 million years. Life retreated to the cracks and the vents and the margins and the thin films of water, and it waited. It did not give up because it has no mechanism for giving up. It simply continued, as it always has, with whatever resources were available in whatever environment remained. And when the ice finally melted, when the CO2 had built to the threshold and the first dark ocean surface appeared at the equator, and the sunlight hit water for the first time in 50 million years, life was ready. The planet that emerged from a freeze was not the same planet that had entered it. It was stranger, more complex, more chemically dynamic, more biologically primed. The freeze had been a filter. And everything that came after, the Ediacaran animals, the Cambrian explosion, the fish and the forests and the dinosaurs and every living thing that has ever existed in the 540 million years since, came through that filter. The snowball melted, and the world began.